I hate to close windows, but here's there. This should work. All right, well, let's start with questions. If there's any questions on what we've been doing, otherwise I'll start talking about some stuff. All right, let me talk about one-day assignment 4 first of all, because there were a few issues with that, and I want to make sure we're clear on that before we kind of switch gears to programming assignment 1. So ODP 4, we were working with a modified type of array. So a structure with 2 pieces. One was an array of 10 integers. The other was just an integer length. And the idea was we could store an array of integers, but also record how many of those integers are actually meaningful. A normal array is simply a collection of memory locations that are contiguous, and there's nothing from looking at an array that tells you how many numbers somebody has actually put in that array. Every location has some collection of 1s and 0s in it. That's the nature of physical memory. So we can't look for an empty element, and we can't do like we do with strings and look for an element with a magic value like 0 and say that's the end of our array. So we created a structure called data that has a length component that says how many things are meaningful in here. And the idea of ODP4 was to make an append routine that lets us add an element to what we think of as the end of this array. So append takes 2 arguments. The first is a struct node, and we've got to pass a pointer to that because we're going to want to change pieces of it. And the second is an integer number that we want to store. All right, do you know what the fence post problem is? Have you heard of this? So the idea is, right, you're building a fence and you've got 7 of these posts. And the question is, how many sections of fencing do you need to build your fence? And you only need 6. So you got 7 fence posts, but there's only 6 things in between there. That's called the fence post problem. And it pops up in a lot of situations. If you look at a street, and street houses are numbered consecutively, so the first house is 510, the last house is 515, how many houses do you have? And it's not just 515 minus 510, it's actually 6. 510, 11, 12, 13, 14, 15. Okay, so this kind of thing pops up when we deal with arrays, and it's sometimes just called the off by 1 problem. So if length is the number of things in our array, which positions in our array are occupied with good data? So if length equals 5, we have 5 things in our array. Those are the 5 locations where our data is stored. which means a new piece of data would in this case go in element 5. So length tells us two things. One, it tells us how many numbers are actually stored in our array. But two, it tells us the index where we should store a new number. And you can test the edge case yourself. If length is 0, the array is empty. The first time we store something, it should go in element 0. So with that, we proceed confidently and we say the following. Position equals arg. And arg is a pointer, so we can't just say arg dot length. We have to say arg arrow length. And we'll put a comment store new number here. And I write code to actually do that store, so arg. And again, arg is a pointer, so to get to this field, we have to say arg arrow numbers. And that's an array, so we can set bracket position pos equals num. Save number at end array. And I put a note in here at the very bottom that says make sure that you increment the length of the array when you're done. So we need to bump up the value of this field, so increment arg length. So my comment there is, remember we have one more number now. And that's our whole append routine. You need to declare variable types and stuff, but that's the gist of it.
That first one where you declare pos as a variable, is that even necessary, or is that
No.
just to make it human readable?
That's just to make it human readable. We could put arg arrow length inside here.
Okay.
I think that's probably what I did. Nope, I actually used a variable. All right, so when you're doing these one-day programs, you follow the instructions, you write your append function, and it will tell you how to build a testable object, right, the GCC command. That's really kind of your last step, or your next to the last step. Before you run the assessment system on your code, you probably want to make your own test bed. You want to make a main program that uses this and somehow checks to see if your code is correct. Because when you run assess, it doesn't really tell you what went wrong if you don't get 10 out of 10. It'll give you a little bit of output, but it's going to be less and less useful over time. Right? That's really a way to double check once you've confirmed that your code is correct. Go ahead and assess it, and the system will run its tests and say, yeah, the code's correct. If you just decide to assess it off, you know, in the very beginning, and it doesn't come back 10 out of 10, then you got to go back and write your own main program anyway. And it's possible you might have a program that doesn't work, and the assess system doesn't notice, and it still gives you 10 out of 10. So it's always good to write the code yourself. For example, one person, they incremented the length in the beginning of this, and then they modified their sum code to start from 1 instead of 0. And they got the thing to work correctly in the assess system, because I didn't test that particular case. So, so how would you write a main program to test this? Something like this. Usual C syntax, etc., etc. Struct data, I don't know, I'm just going to call it X. X.numbers, let's see. I want to start off with an empty array, so I'm going to set the length of this to be 0. And now I want to add some numbers to this, so I'm going to say append. I need to pass the address of my struct data, so I'm going to say ampersand x, comma, and I don't know, I'll just give it a 5. That should put a 5 in the first position of the array. And then I can say append ampersand x 42, and I can say append ampersand x -1. So at this point, I should have 3 elements in my array, a 5, a 42, and a -1. I would run this in the debugger, put a breakpoint right after this, and then just look at x. Just say p space x, and it should show you that it's got an array, it should show you the 10 values in that array, and it should show you the value of length. And you're hoping that length is 3, and the first 3 elements in your array are whatever the 3 numbers are that you inserted. If that's working, your program is probably correct. If that's not working, if length is 4, or length is 2, or length is 0, you got something wrong. Okay, but you've got a test bed that you can use to help pin down exactly where the problem is. So now what do? Put a breakpoint at append, and as soon as you get into append, take a look at x. Make sure it looks reasonable. Step through the code and make sure that it's doing what you expect. And somewhere it's doing something different from what you wanted. All right, let me talk about PA1, since we haven't actually talked about that since we've been gone for a week. So on Monday, we were talking about data structures, and we built up to something that I said was called a linked list. And let me put a picture of this back up here. Did people have a chance to watch yesterday's video, by the way? Okay, so I'm not going to go into too much rehash of that. So we have data that we're trying to actually store in our linked list, and our trick was we added a field called next that told us where the next piece of data in the list was. So we didn't have to assume it was always the next location in the array. We could bounce around the array. And there's this third field that we call valid, which basically says, is there an actual part of our list stored in this location? That's so that we know if we want to get a new node, which nodes are available, which indexes in our array are available. So this first entry we call the sentinel, and it's not actually part of our list. The data in this node is not part of our list. The only purpose of the sentinel is to point to the first node in your list. So let's suppose that our list contains the numbers 10, 20, and 30. So we don't care what the data is, the sentinel is valid, and I'm just going to assume that this was built with numbers coming in that order. And so this might be what our list looks like right now. So the sentinel says our first number is at index 1, and that number is a 10, first number in the list. The second number in the list is at index 2, and that value is 20. The next number in the list is at index 3, and that value is 30. The next number in the list doesn't exist. This is the end of the list. And we're using these first 4 locations in this array, and these other locations are all marked as invalid, so they're all available. All right, so this was our basic setup that we were pretty close to on Monday, and that we talked about in the video yesterday. So programming assignment 1, you're writing code to implement a linked list using this kind of structure. So the first thing is you're going to want to define a new type of structure called a node that contains these 3 fields. So an integer data, an integer next, and an integer valid. The next thing is this -1, I'm asking you not to hardwire that into too much of your code. You don't want magic numbers in 50 different places in your code, because if for some reason you need to change that -1 to a -42, you got to go through your code, you got to find all the -1s that are being used like this and change them to -42, and it's a pain. So I've asked you to use a define, make a symbol called myNull, and set that equal to -1. So this statement starting with a number sign will do that. And then whenever you want to store a -1 or check for a -1, don't use -1, use myNull.
Should the next be a pointer to int?
Nope, it's just an int. Right? It's a 1, it's a 2, it's a 3, which we're interpreting as the index of the next thing. But that's exactly what we're doing. We're faking the behavior of a pointer. All right, this stuff, I would put this in a .h file, because pretty much every piece of code you write, you're going to need to know what a node looks like, and you may need to know what myNull looks like. Probably not so much this, but you're definitely going to need to know what a node looks like. So put this into something .h. I wouldn't call it something, but call it something else. So that goes in a .h file, and in your .c file, whatever it's called, include double quote whatever your h file is called. When you say #include, what that does is it opens this file, it reads its contents, and it plops it right here into this file. So it saves you from taking all of this and actually typing it into each of your .c files. And usually the only thing you find in .h files are definitions, declarations of structures, prototypes of functions, things like that. You usually want to avoid putting actual code in here. For example, I would not put your init routine in this .h file, because every time you include something .h, it's going to include that code for init.h, and the compiler is going to get confused. Linker, actually. All right, so if we include something .h, we've got the structure defined. We can start talking about struct nodes. So, struct node, and for some reason I use lowercase l's in here. I don't know why. Well, I do know why. What I don't know is why I didn't change it. Oh, I called the list. Okay. That's fine. This is our declaration in our main program. So let's think of this as main. This is our declaration of where our linked list is going to sit. It's just an array of struct nodes. So when we do this, we get a chunk of memory that looks like this. It's got 100 rows. Each row has basically 3 pieces to it: data, next, and valid. Now the first problem is we don't know what is actually stored in each of these boxes initially. Probably just gibberish. And what we really want for an empty list is we want to make sure that this first index has a next value of my null, -1. We want to make sure that this node is valid, and we want to make sure that all of these other nodes are marked as not valid. So that when we ask for a new node, we can take any of these, because we'll check and say it's not in use right now. So we need to do some initialization on this array. That's what your init function does. So you need to write a series of functions. The first one is called init. And init takes this array as an argument, and it does those initializations that I just described. Sets element zeros next to my null, sets element zeros valid to 1, sets all the other elements valid to 0. But you want to bundle that into a function and call it init. Why? So that in your main program, instead of having a for loop and all this special magic code, you just say init list. Okay, this is back on this theme of modularizing. So as I mentioned in the video yesterday, these 5 routines, init, add, print, delete, and search, that's your interface as a main program to this data structure. Your main program should not have to worry about this. It shouldn't have to know that this is an index to the next element, and if it's equal to -1, we're at the end of the list, and if it's 0, it's not part of it. That's all under the hood, okay? Your main program interacts with this list only through these routines: init, search, delete, add, and print. So create the structure, throw it into .h, write an init routine. That's your first task, and that ties into the one-day assignment that's due tomorrow morning. So let's pop over to that, and then we'll come back and look at these routines more. And please, please, please ask questions on the way if questions come up. So one-day program 5 is basically testing your init function. So write your init.c, I haven't written it here, good. Write an init.c that takes an argument of type struct node star. Right, so what does this look like? Void init struct node star LL, for example. Right? What we're passing it is an array of something, which means what we're passing it is a pointer to that something. So in our function, we can declare the argument to be a pointer to a struct node. Okay, so you prototype it like this, and you declare it like this when you start actually writing the function. So write your function, write the code to do the necessary initialization, put that into an init.c, and then test it yourself. So make a main program that creates a list, calls init, put a breakpoint right here. After you come back from init, say p space list, and look at what its value is in memory. And GDB is nice enough if you give it an array of structures, it'll actually show you the pieces of a structure. You don't have to take apart memory barehanded. And make sure that, this is a -1, this is a 1, these are all zeros. And while you're in there, observe that the other locations probably have gibberish in them, which is what we expect. Okay, or do something to test it manually. I like GDB because you're going to need to spend a lot of time in GDB in this course. But you could also, make a for loop that just prints out these 3 fields for each element in the list. And then you could stare at that 100 lines of output and make sure it looks correct, and so on. Once you think your init function is working correctly, go ahead and make a test bed. So link it up with /temp main.o, and then say assess main. And I only put one test in, so it's all or nothing. If it tests correctly, then go ahead and say G to run the graded test. And that's also one test, and it should be all or nothing. Does that make sense? Okay. Let me mention something I mentioned in the other class too. So you're running your assess and something happens and your session goes away, like so. So you come back and you log in again. It's not messing up for me. Well. Let me see if I can replicate this. No attention to it. All right. Well, I can't replicate it right now, but some people are having a situation where they try to assess their code and the network connection goes out, or for some reason the PuTTY session exits. And when you come back in and you try to reassess, you may or may not get an error from it. I don't think I'm getting an error because I think I set my limits higher. But you get a message about too many threads or out of resources or something like that.
You actually have to run the test for it to work.
Oh, really?
Yeah. It prompts to start that test to test. It gives you 8 or 10 usually.
Yeah, I think my limits are higher. All right, so if you get to that situation that I can't seem to replicate, but where assess is giving you errors and is complaining about what's going on, type the following command: ps space -fu followed immediately by your user ID, no space. So ps-fu nick. And chances are what you'll see is somewhere there's a process called assess. This cuts off at 80 characters, unfortunately. But somewhere you'll see that you already have an assess session running.
It's not just assess, it's actually if you have 2 bash scripts running, so you have multiple.
Oh, really?
Yeah, if you have an actual list of enough memory to run.
Okay, I need to bump up those limits then.
I was having that issue because I had screen running,
Yeah,
just from inside of screen with another tab or something else that wouldn't let me in.
I'll bump the limits up tonight. Because I think I got it set to like 10 processes or 5
Put it
processes.
really, really high. We want to
Yeah, I'll make them limitless. So another option is finger space user ID. And that will tell you all the times that you're logged in. So let me just cheat. Start a duplicate session. Okay, so if I say finger Nick, it'll show me that I've got 2 sessions. One of them has been idle for 36 seconds, the other's been idle for 4 seconds. This will usually say like an hour or something, right? If something died and you went away and you came back and it's still out there, this will be some big idle time. So this is the terminal. It's a synthetic terminal that it thinks I'm logged in on. So PTS4, I've got a session sitting that's idle. And if I do this later, that will just get more and more idle. So that's been idle for 1 minute and 6 seconds. PTS10, that's where I just typed finger. Okay, that's my current session. 1 second idle was just the time between hitting enter and getting that. So now do your ps-fu user ID. And you'll see a series of entries. Some of these are on PTS4, some of these are on PTS10. PTS10, that's my bash session, that's my ps command. PTS4 was an old bash session, and it's also where I was running SS. Okay, so you need to get rid of that process. So, find the line that has SS, and I've got 2 of them in here. Find the PID, and it looks like PID 36396 and 36397. And then say kill space and whatever the PID is. So I'm going to say kill, and I'm going to kill 36396 and 36397. You can do it twice or 1 per line. And now if I do my PS, oh, my SS is still running. Say kill -9. And those PIDs. Now if I do the PS, those SS sessions are gone. And if you want to kill your login session, right, that was PTS4, I can kill 36377. And now that login is gone. So if you're finding that issue where it's not letting you run your SS, do some snooping around, see if you've got a background session running. And if you do, go ahead and get rid of that. All right. Back to our data structures. So any questions on one-day programming 5? You got to write your init routine anyway, so write that first and put it in the test bed, make sure it works.
For some reason I'm getting an error with trying to include something. First of all, is it supposed to be the angle brackets, not quotes?
No, angle brackets looks in a certain directory, a system directory. Double quotes looks in your current directory. Yeah, that's the trick. Angle brackets look in /user/include.
So you don't have to compile the something.h before you include it, right?
Correct.
Okay.
Yeah, when you say include, it's basically pulling that code and pretending that it's inside your thing that you included it in. So if you compile that .c, it'll compile that code then.
Perfect.
All right, so your first goal is to create these 5 routines, starting with init. I'll probably post another one-day program either tomorrow or Friday. I'm not sure which, but it will probably be another piece of one of these, maybe. So look on Canvas, and I'll send an announcement if I do, or I might just wait. All right, so your first goal is to create these 5 routines. This is how you're going to interact with your linked list. Init does what we've been describing. It sets up an empty list. Add will take a number and a list, and it will add that number to the list, but it adds it in order. And we're going to go through the pseudocode for that very shortly. So it basically inserts something into the list. Print will just print out the elements in your list on one line, separated by spaces. Delete will remove a node from your list. And search will search your list to see if there's a node with a given value in it. And if there is, it'll return a 1. If not, it'll return a 0. All right, under the hood, you probably want a pair of helper routines. Well, you definitely want a pair of helper routines that are required. Get node and release node. So when you want to add a new node to this list, for example, we want to add the number 50, the first thing we need to do is go through here and find an entry that's not being used. So start at the beginning and check your valid flags. Find the first entry where the valid flag is 0. Set the valid flag to 1 and return this index 4. That's what get node does. If I call get node again, it should return a 5. If I call it again, it's probably going to return a 6. So each time you call get node, it returns the next node that's available. It sets the valid flag to 1, and it returns that index. If there's no space left in your array, if you go all the way through the array and every single entry is already valid, get node should return -1. -1 or 0? Yeah, return -all if there's no space left. So that's your flag saying I don't have room in my array for anything else. Release node does the opposite. Release node, you give it an index and it clears the valid flag. So when you're done using what was stored at element 5, for example, if you just deleted it, I could say release node 5 and change that valid from a 1 to a 0. All right, any questions about the main program? We talked about this extensively on the video. It's really just a test program you're turning in with your functions that I'll use to test your code. So it's a little command line interface. You can say insert a number, print my list, search for a number, delete a number, or exit the program. And it's also a good way for you to test your code as you're developing it. If you write your main program early, you can use it to exercise your functions. Any questions on deliverables? Comments, etc. That was all discussed yesterday. All right. Let's see. Let's take a 5-minute break, and then let's start talking pseudocode for how we actually do some of these functions like add, insert, and so on. I'll leave that up there. I'll get rid of this. Take 5 minutes. We'll come back here, and we'll start at 10 minutes till. So let's look at how we actually manipulate this structure to do some of these list operations. And we've already talked about init. Let me talk about the add routine. So again, I'm going to suppose that this is what my structure already looks like. So my list consists of 3 integers, 10, 20, 30 in that order. And suppose what I want to do now is insert a 25. All right, here's how I go about thinking about this. Forget about the code for a moment. Just think about this structure. Just a collection of numbers in an array. Each entry in the array has a triple of numbers. And this is what it currently looks like. What steps do I go through as a human to insert a 25 into this list? Without being too clever. Because I know 25 comes before the 30, so I could look at the 30 and back up. But let's not be clever, okay? Let's think like a computer. Well, I know the sentinel always points to the beginning of the list. So I'm going to look at the sentinel, index 0. That's where I always start. And it tells me my first data node is at index 1. So now I look at index 1, and I see the number 10. 10 is smaller than 25. So my 25 is going to come somewhere after this entry. So I want to move on through the list. So I look at the next field of index 1, and it's a 2. That tells me my next entry is at location 2. So now I look at location 2, and I see the data, and it's a 20. 20 is still smaller than 25. So I look at the next data, and that's a 3. So now I look at index 3. And I check the data, and it's a 30, and 30 is bigger than 25. I'm looking at location 3. I want to insert my number right before that. So what I really want to do, so this is where I'm looking. What I really want to do is insert my new node after the previous node and before the node I'm currently looking at. The first complication is I don't remember what node I was looking at previously. All I know is I'm looking at node 3. I have no memory of the fact that I was looking at node 2. So I'm going to change my algorithm a little. I'm going to remember two things. I'm going to start off and I'm going to say this node, that's where I'm going to begin. And next node is going to be the next node in the list. So if the data at next node is smaller than what I'm trying to insert, I know I'm going to insert somewhere after this location. So I'm going to change this node to point where next node is pointing, and I'm going to change next node to point to this node's next field, in this case 2. And I'm going to check next node's data. And it's still smaller, so I'm going to do the same thing. I'm going to set this node to point to wherever next node is pointing, and I'm going to change next node to point to this node's next, which is 3. And I'm going to check next node's data, and now I find a number bigger than 25. Freeze everything. At this point, my goal is to create a new node with 25 in it, and sandwich it between this node and next node. Everybody agree? And how do I do that? Create a new node, get its index, that's what getNode does for us, say it's a 4, and I'm going to want this node's next value to now be 4. So that this node, which comes before the 25, is now pointing to the 25. I'm going to want to set this new node's next value to point to next node. And after I've done that, the 25 will be sandwiched in between the 20 and the 30. All right, that's the algorithm of how I'm going to do this insertion. Let's look at some pseudocode. So I started off with this node was 0, that's the sentinel, and next node was the sentinel's next field. And then if next node, if this next node's data, so list bracket next node dot data, if that's less than, so let's say insert list new number. If next node's data is less than new number, then I want to just move down the list. So what we said we do is we take this node and we set it to point to whatever next node is pointing to. So this node equals next node. And next node equals list next node, sorry, list right, next node is just whatever the next node is on this node. So let's run this from the beginning and make sure it makes sense. This is 0. Next is list bracket 0 dot next, that's a 1. Next dot data is 10, that's smaller than 25, so set this equal to next. So this is equal to 1, and set next equal to list next, which is list 1 dot next, that's a 2. So next point's right there. And then come back up here and do this again. So something like a while loop. List next data is 20, that's still smaller. Set this to a 2, set next to next field of next, which is 3. Next goes down there, come back up, check this again. List next node dot data is 30, that's no longer smaller than new num. It's bigger than 25. So kick out of this loop, and at this point, insert new num between this node and next node. All right, how do we do that insertion? Let's do this by hand again, and then let's do it in code. So find a new node that's not in use, call your get node routine, it's going to return a 4. It's going to set the valid bit to a 1. Store new num into this data field. Take this node next and have it point to your new node. So change this to a 4. And take your new nodes next and have that point to what was your next node, 3. And we're done. Our list begins with a 10, that points to a 20, that points to a 25, that points to a 30, that's the end of the list. So what's the code look like for that insertion operation? So let's insert the node. So new node, what did I call it? Get node. So that should return this number 4. And then we had set the data field, so new node. Dot data equals new num. So that stores our 25. And then we wanted whatever this node was, which comes before the 25, to point to our new node. So list this node next equals new node. So that sets this up to point to our new node. And lastly, our new node's next field should point to whatever the next node is.